Yeah, good evening, everyone. Let's start off. The last thing that we did was the force on the curved surface. Cams on, everyone? Great. Let's go ahead with the problem. So we have some liquid here. Inside this liquid, we have an ice block. And density of ice is 0.9 gram per cc. Case 1, it's pure water. Density is 1 gram per cc. Case 2, let's say it is some water plus alcohol. So the density will decrease actually. So it's 0.95 gram per cc. Let's say case 3, it's a salt water. So density is 1.05 gram per cc. If ice melts completely, what happens to the liquid level? Increase, decrease, remain same. 3 cases. Let's get this. Mm-hmm. Think. I'll give a minute, then I'll see. No, Srihari, that is wrong. Think. Don't just give random answers. Think for a moment, everyone. The first one is the standard question. When the ice melts, what happens to the water level? I just made up the other 2 cases. Case 1 is fine. So first of all, let's see what is happening. Case 1, when you put it in a regular liquid, see, when this distance was x, I hope you remember the formula. X is equal to density of the body by density of the liquid into L. This we proved in the before. Next thing, when you take an ice block, and when this melts into water, mass remains same. Mass of ice is equal to mass of water. So this is 0.9 gram per cc. So density of ice, volume of ice is equal to density of water, volume of water. So we can clearly see the volume of water is 0.9 L cube. So whenever an ice block melts, you don't get the same amount of volume. You actually get less. Is that making sense? Now look at the three cases. Case 1, density of water was 1 gram per cc. So the Xka value will be 0.9 L. Now imagine that ice block was removed. So you would get a cavity like this, isn't it? So this height of this cavity is 0.9 L. So what will be the volume of this? The volume of this cavity will be 0.9 L cube. Make sense? And what you're doing now, you're taking this water which got melted and you kept it in this cavity. So the size of the cavity is 0.9 L cube and you're putting this water 0.9 L cube. So the water level will remain same. Volume of cavity is 0.9 L cube. Therefore, if you see, the water level remains same. Is that making sense? What I did? I found out how much space the ice block is occupying. It is occupying only 0.9 L cube. When the ice block melts, how much water are you getting? You're getting only 0.9 L cube. So if you take this water and fill it up, it exactly fills the space. What about the case 2? In case 2, density of that liquid, whatever was 0.95 gram per cc. That means you will get X will be greater than 0.9 L. That means volume of the cavity exceeds 0.9 L cube. That means this gap now, volume, is greater than 0.9 L cube. Now, if you take this liquid here and pour it here, it won't fill the whole cavity, isn't it? It won't fill the whole cavity. So the water level decreases. In case 3, it is 1.05 gram per cc. X will be less than 0.9 L. So volume of the cavity will be 0.9 L cube. So in this scenario, the volume of the cavity is less than 0.9 L cube. See, but remember, no matter when ice melts, it will always give pure water of 0.9 L cube. If you take this and fill it up, it is definitely going to overflow. Increases. Is that clear, everyone? Is the logic making sense? So the two questions you need to ask: when the ice block melts, how much water you're going to get? Now remember, whenever ice melts, you always get pure water. Is that clear? Easy. Let's see the next one. This was a JEE 2006 question, the year which I wrote. Let's see how to do this. Look at the question here. We have a wooden cylinder of diameter 4r, height h, density rho by 3. So the cylinder ka rho by 3 is kept on a hole of diameter 2r of a tank. There I drew the picture again, see here. So we got a cylinder here, and again, see I'm drawing it for you. So there's a gap like this. Are you getting how is the picture? So there is a hole like this at the bottom. Now what someone did, you took a disc and you placed on top of it. Let's see if I have the fresh picture. No. Clear. So this cylinder is there, and someone kept a wooden plank like this, a wooden block like this, and then you started filling the liquid. Yeah, and you can see the heights here. H1 is the height of the liquid above the base. H1, capital H is the liquid here, and H2 is the height of the block. So the first question is, if the liquid level starts decreasing slowly when the level of the liquid is at a height H1, the block starts moving up. Then find the value of H1. Answers are given, but yeah, you can give it a try again. Let the cylinder is prevented from moving up by applying a force, and the water level is further decreased. Then height of the water level H2 for which the cylinder remains in the original position. So there are two questions here. So the meaning of this word, right, block starts moving up, meaning it loses contact with this part here. Yeah, the picture is not great, but unfortunately, that is how it was. But I hope the picture is clear at least. Anyone didn't get the diagram, please ask, I'll explain. Let's do the 24. So initially, there is some water level here. As you start decreasing the water level, at a particular height H1, the block started moving up. What is that height H1? Then second part of the question, he's saying someone is holding this block with force, and then you kept on decreasing the water level. At a particular water level H2 here, the block will not go up again. Means you need not apply any force. So basically, there are two heights where the normal reaction just becomes zero. Get the first one. Second one, I'll show you the picture. Remember, at the bottom, this is exposed. Huh? This is an atmosphere. Anyone not clear with the picture, please ask me. This was JE 2006. Always start with the free body diagram. And the answers, so I marked it anyway, but you can figure it out. I'll just draw the picture again. So I'll just draw the FBD. Let's hope you got that. Most of my friends goofed it up actually. They took Bayern force. Bayern force won't work here. Remember, I told you the bottom part is not completely filled with liquid. You have a different thing there. So that was the main idea there. This was the bigger picture there. Now, in the first case, the liquid is here. So this height was H1. Now look at the forces. From the top, P naught plus rho g H1 into area 4 pi r square. Why? The diameter of this thing is, diameter is 4r, so radius is 2r. From the bottom, we have atmospheric pressure P naught into pi r square. Your own weight mg. And on top of it, remember the liquid is also exerting force from the sides. This would be P naught plus, what is this height here? This height is, height of the block is H. P naught plus rho g H1 plus h into 3 pi r square. Does that make sense? Why 3 pi r square? Because this part here is exposed to atmosphere, the remaining part still is having liquid. And there is also a normal reaction N, because you're sitting on top of it, there's a normal reaction. Now, if you look at all the forces acting here, the upward direction, P naught pi r square plus P naught plus rho g h1 plus h 3 pi r square plus normal reaction must balance mg plus P naught plus rho g h1 4 pi r square. Since you are losing contact, n will be 0. You can clearly see P naught pi r square ka term will cancel on both the sides. So you'll be left out with rho g h1 plus h3 pi r square. What is the mass of the block? Density is rho by 3. So I'll just keep it for some time. This is rho g h1 4 pi r square. So that is rho g h1 rho g h3 pi r square. mg will be rho by 3 pi 2r whole square hg plus this rho g h1 3 pi r square and rho g h1 4 pi r square, that will subtract. You will end up with rho g h1 pi r square. Rho g pi r square will go off everywhere. You will be stuck with 3h, 4h by 3 plus h1. So we get h1 is equal to 5h by 3. Yeah, 5h by 3. Are you clear what I did? Simple free body diagram. There's nothing there. The top part has one pressure. The bottom part will have two pressures. One because of atmosphere and one because of the liquid, which is covering from R to 2R. Yeah, you should use pressure. You can't use buoyant force here. All clear with this? So directly you can't say there's a buoyant force acting on that because the bottom part is not completely with liquid. What about the second picture now? Now let the cylinder is prevented from moving up. You kept on decreasing the water level. So let me show you the picture. So this time the liquid level is only till here. You're getting it? It came beyond. So from here to here, this is H2. Now he's saying for this H2, the block again, the normal reaction just becomes 0. Same story. Now the force will be P naught into, this is the B part of the question, 4 pi r square. P naught into pi r square. We have your mg. This thing will be P naught plus rho g h2 3 pi r square. And this will be the normal reaction N. Equate them. N is 0, P naught ka term will cancel. You'll end up with mg is equal to rho g h2 3 pi r square. This is nothing but rho by 3 pi 4 r square g hg. We get h2 is equal to 4h by 9. That. But are the pictures clear, everyone? Not a tough question. You just have to draw a free body diagram. But like I said, you should understand what is happening there. You just have to be careful with the forces. That's a paragraph. Got this? Any doubts on the free body diagram? So this is the first part. So this is how the picture was looking. The height liquid was above the that cylinder. In the second case, the liquid came down. So meaning from that height H1 to H2 in between this scenario, the block is trying to lift off. You have to apply force to keep it at rest. All clear with this? Others, do keep your cams on. Let's see one more. Let's see something more complex than this. This is still an easy one, but you got an idea. You can't use buoyant force here. Let's say we have a container with a hole. Filled with liquid. Now this hole, right, what you did, you closed it with a solid cylinder. So you basically you plugged the thing with a solid cylinder here. This radius is R. This radius is 2R. This is R and this is also R. And density is rho by 3. And then you started filling the liquid here. Density of the liquid is rho. So as you keep pouring liquid, right, at some point, what will happen? This thing just lifts off. Outside the pressure is P naught. So basically a solid cylinder, solid cone, blocks a hole at the bottom of a tank of radius R. Right? Find H when when the cone lifts off. If you keep pouring liquid at some point, the cone will just lift off, the hole will open up. Yeah, kind of the same as the previous question. I just changed the shape. Is the question clear? We have a tank filled with liquid. The total height of the liquid is H plus R. There is a hole at the bottom of radius R. You kept a solid cone and you stuck it inside. So it is just blocking the liquid from leaking out. Density of the cone is rho by 3. Density of the liquid is rho. Find the height of the liquid when the cone lifts off. Anyone didn't get the picture, please ask me.
सर नीचे भी पी नॉट है ना?
Uh-huh. Nineteen R by 9. Near Samyak. Take a minute. Let's get the FBD first of all. First draw the FBD, you will see something. Like I keep saying, if you can draw your FBD properly, half your job is done. Let's see the free body diagram. Let's see whether you got the free body diagram right. Look at the picture here. So what are all the forces acting here? One from the top. This will be P naught plus rho GH into 4 pi r square. Then, now the problem here is the liquid is also pushing from the sides. And the pressure is not constant. So there is a force due to the side walls, which is upward. And you have your own weight mg. And outside, if you see, there is a constant pressure P naught. Is that making sense? These are all the forces, right? So you can't use buoyancy force here because that lower part and the side forces are messed up. Now, the green one is easy to find because we can use projected area. Remember, if the pressure is constant, I can use projected area, P naught into pi r square. But what about the side walls ka force? नहीं होता. Right, Anita. How did you find the side walls ka force, right, Anita? Did you include the side walls ka force? Included, okay. How do we approach this? We can't use projected area for side walls. Pressure is not constant. So listen. Now, if I just draw this thing, right? So for this P naught, because the pressure is constant, you can directly say it is P naught into pi r square. So this is your projected area. Remember, you can use projected area only when the pressure is constant. P naught is constant. You can do that. For the side walls, you can't do that. P naught plus rho GH 4 pi r square. Mg and side walls. I'll just call it FSW. So yeah, if I can find F side walls, my job is done actually. I'll get the answer. The F side walls plus P naught pi r square has to be equal to Mg plus P naught plus rho GH 4 pi r square. Mass though I can find. What will be the mass? Mass M will be 1 by 3 pi r cube, that is 2r ka square. Height is 2r into rho. That's your mass. So basically, I know everything here except F side walls. Now, for the side walls, listen to this thing. I have an idea there. I don't want to use integration. Suppose, forget about that hole there, okay? Ignore the hole and you take a shape like this. So consider a shape like this. Basically, it's called a truncated cone. You removed that thing. So consider a truncated cone completely immersed in the liquid. And the volume of this thing will be the volume of the full cone, which is 1 by 3 pi 2r whole square 2r minus that small cone 1 by 3 pi r square r cube. So this is 7 by 3 pi r cube. This is the volume of the cone. Now this is my idea there. Now I don't care what is acting here. There is a force acting from the top. There's a force acting from the side walls. And there is a force acting from the bottom because it is completely immersed, right? This is completely immersed in the liquid. It has nothing to do with the previous problem. I'm just putting it. So now here, what I can do, so this forces, right? So there is a force from the top. I'll just write F top. There is a force from the bottom. I'll call it F bottom. And there is a force due to the side walls. I'll call it FSW. Now, if you guys remember, F bottom plus F side walls minus F top, isn't this nothing but the bind force? Do you guys agree with that? Isn't that the bind force? That is the definition of bind force, isn't it? The difference in pressure between the lower and the upper surfaces will create an upward thrust. If this whole thing was immersed inside the liquid, these three forces would give you the bind force. Now I know this height actually, this height is h and this height was r. So F bottom will be on this area here, P naught plus rho g h plus r pi r square. F top will be P naught plus rho g h 4 pi r square. And the buoyancy force will be density of the liquid into volume 7 by 3 pi r cube g. Is that making sense? I know everything here. So from here, I'll get the F side walls. I can take this F side walls and dump it in this. I'll get my answer. Are you clear with this? So we can calculate F side walls from here. Yeah, a little working. How much will that be? Rho 7 by 3 pi r cube g. Here they have to subtract. So P naught pi r rho g h. Nothing will cancel here actually. P naught 3 pi r square. That will be rho g h 4 pi r square. Rho g h 3 pi r square minus rho g r cube. There, that's your force due to the side walls. Actually, I could have found, Fs minus F top. And here also I would have written this as, F side walls minus this is F top, isn't it? That would have been cancelled much faster. Making sense. So yeah, you have to take this and substitute here. कुछ simplify होगा क्या? This thing, there should be a pi here, no? Yeah, that would be 7 by 3 minus 1. That's 4 by 3. This is, yeah, we got a stuck there, h though. Yeah. 4 by 3 pi r cube g rho plus 3p naught pi r square plus 3 rho g h pi r square. That's your force due to the side walls. Just a matter of solving now. Take average. What will take average, Ray? Arya?
Sir, I thought of taking average of the pressure at the top and at the bottom to find force on side walls, like COM kind of thing.
That will give you
Because
maybe that might give you the horizontal component. Vertical nahi aayega.
mm,
Remember that we
okay,
did, if you remember that shape, when you have a shape like this, the horizontal force acting on this is the pressure at the center of mass into area.
okay.
That we proved for horizontal surfaces. Na vertical ka we didn't prove anything.
सर एक्चुअली आई वाज थिंकिंग कि मैंने वो साइड वॉल्स को हटा के वहाँ का पानी देख लिया। अब वहाँ का
Hmm.
जो पानी था उसके ऊपर साइड से फोर्स लगेगा एंड दैट
Uh,
फोर्स विल बी द कंपोनेंट ऑफ द द वर्टिक हॉरिजॉन्टल कंपोनेंट ऑफ द फोर्स व्हिच इज एक्टिंग ऑन साइड वॉल्स।
कर सकते हैं वो भी. That would look something like and that is also work only actually, because if this is the liquid, na, then you have to say the force due to the side walls and the force at the bottom, and this mg भी लेना पड़ेगा ना.
सर फोर्स ड्यू टू साइड वॉल्स तो मेरे अकॉर्डिंग जीरो होना चाहिए जस्ट लिफ्ट ऑफ के टाइम पे।
क्यों?
सर क्योंकि
अरे,
नॉर्मल
why will the God, normal reaction will be zero, right? This contact will be zero. Why will you're meaning to say liquid and the surface will lose contact with each other? Liquid will always keep touching the cone.
Oh my bad, I got it confused. Sorry, sir.
नहीं, वो भी अच्छा idea था, but I think that also will involve work only. But
Sir, I
Anvita, what did
try
you
after
do?
class and do.
Anvita, did you do this way? Did you do something else?
No, first I started integrating, but then I remembered that we don't have to integrate in this, and I took buoyant force only.
यही किया basically.
Yeah.
Then yeah, you can dump it here. This is big board to solve this.
When I told you the answer, I'd integrated, but then later I
Okay,
realized that I can do it from that method.
integration से fast आएगा आंसर?
नहीं, but आ गया.
आ गया था, ठीक है. P naught plus rho g is 4 pi r square. Now, instead of taking P naught plus rho g is 4 pi r square, I should have taken as f top. That would simplify a bit. ठीक है. Anyway, अभी ले लिया तो क्या करेंगे? Let's dump it here. 4 by 3 pi r cube g rho plus 3 p naught pi r square plus 3 rho g h pi r square. This is your f side walls. Plus p naught pi r square. Mg will be rho 1 by 3 pi r cube g plus p naught plus rho g h 4 pi r square. Great. So this 3 p naught by r square, this p naught by r square, this p naught will cancel. And this is 4 by 3, that is 1 by 3. So that would be pi r cube g rho. This is 3 rho g h. It will go that side. That will be 4 rho g h. So that will be rho. I goofed up something, I guess. Yeah, rho by 3 tha. Yeah. So the block is rho by 3. That's 4 by 3 minus 1 by 3, 12. That's 4 by 12 by 9 minus 1 by 9. What the hell did I get? Where did I mess up the calculations? We need to prove, but you're getting kx type error, yeah? Nay, God. You'll not get that. When you take the ring here, if you take a depth x now, this area will be 2 pi x dx. Pressure is rho gx, that is an x square. Integration ka term should be x power 1. You're getting?
Sir, I was
Pressure
just
into
talking about pressure, not the force.
Nay, see, when we took this areas, if you remember, in this case, na, if you remember, we got P naught plus rho gx into L dx. Na. This was x power 1 function, integration. Mein. If integration was x power 1, you can take average.
Okay,
ठीक
sir.
है. Where did I mess up something here? That's 4 by 3. Seven था. नहीं, one only ना. Someone can see where I messed up. Let's remove that pi r square everywhere actually. Pi r square row will go off. 4 by 3 r plus 3h so gr square is equal to 1 by 9r plus 4h. H is equal to 1.
सर
11r by 9. हाँ रे
सर वो 8/3 नहीं होगा, ρ/3 इंटू 8/3 पाई आर क्यूब जी।
हाँ वो 8 होगा सही है. I am messing up that. So then this will be 8 by 9. Then it will go that side. So h is equal to 4r by 9. You're right. That was a mistake. But is this idea clear, everyone? How to find the side walls without integrating? So in this whole question, that is the main thing I wanted to show you. But rest of the question is just if you see pure FBD only. Please have a look at this. Remaining is just solving. It is lengthy. Clear with this? Pratyasha? Clear? Vedika? Devanshi? All got this? Next thing. Stability of ships.
Sir,
Yeah.
sir, I think there is a possibility that the cone can even lift off without the water being over it.
It can lift off when it is down also, no? हो सकता है. But question में तो I gave you the picture, ना?
I mean, H can be negative, so ठीक है.
हो सकता है, हाँ. But if H is negative, na, this FBD only won't work. You have to draw a new FBD.
Yes, sir.
So directly you won't get. You have to change the picture and then check. Now, next thing. So when you design ships, right, what are the things that you have to take care? For example, see, when you design a ship, remember I told you the mg will act at the center of mass, but whereas the buoyancy force will act on the center of mass of the displaced liquid. So if you take the center of mass here, and let's say the buoyant force is acting here. Now see what happens. If the ship tilts even a little, which is the case normally when you have these waves and all, right, the ship tilts a bit. Your center of mass will be somewhere here. Your buoyancy force will be somewhere here. You can clearly see they form a couple kind of thing, and the torque will be actually in this direction. So even if the ship tilts little bit, this will rotate even more and the ship will completely topple. This is unstable equilibrium. So when you design ships, you have to make sure the center of mass is not above the center of buoyant force. So the ships are actually designed this way. So they make the ships heavier at the base. So the center of mass needs to be as low as possible. The buoyancy force will be upward. Now see what happens. You know, if the ship tilts a bit because of the waves or whatever, mg is here and the buoyant force is somewhere here. Now this is a restoring torque. This is a stable equilibrium. Therefore, for stability of the ships, the center of mass has to be below the center of buoyant force. That is the reason when they design ships, right, they keep the engine room, they keep the cargo room, all that wastewater, all that stuff, right, they keep it at the bottom of the ship. They try to make the ship as heavy as possible at the bottom. So if you see, a cruise ship is actually less stable. And still, it has a lot of weight. The problem is, in a cruise ship, right, everyone wants to stay on the higher floors. If you've ever been on a cruise, you must have seen, right, they have 15, 13 floors. Right. So, and if you see the engine room, the restaurants and everything, they try to make it heavy as much as possible by keeping it in the base. The most stable ships are the oil tankers. So if you ever seen in the super carriers, they call it, they carry large amount of oil. These things are pretty stable because it is completely filled with oil and most of this thing is just heavy. There's nothing there. Center of mass has to be below the center of buoyant force. Here, If people stay at the bottom, it will be very rocky and all. It's not comfortable ride, and you don't get to see anything outside. Let's see one more. We have a wooden stick here. This is immersed in a liquid. Density of the liquid is rho, and density of the rod is rho by 3. T is the tension. Find tension and angle theta. So normally if you had just thrown this rod into the water, it would have floated. It is a wooden stick. So one end you tied it to a string, and the other side is just floating in the water. Find the tension in the string and find angle theta. Meaning, if I have to make it a little simple for you, I'll ask you this: find this length x which is inside the liquid. Start from there. Find how much part of the rod is inside the liquid. Hope the question is clear. Start with the free body diagram and assume this is x. Start from there. Let x part of the rod be inside. How do we approach this? Let's see, did you get the free body diagram? So let this part of the rod be immersed here, the green one. Let this be x. What are the forces? Tension, your own weight mg, which will act at the center of the rod, which would be L by 2. And your buoyancy force here, which will act at the center of mass of the displaced liquid. So that's x by 2. Because if that total length is x, it should be at the midpoint of that green part. Is that clear, everyone? That's your free body diagram. Now what? Tension must be mg minus buoyant force. So somehow if you can find that x, my job is done. Try. I'll give you a minute or two. Now, how do you approach from here?
Sir, what is the density which is given?
Rho by 3 for the rod. Let's see. We have to balance the torque. Because if this angle is theta, let's take torque about this point. Torque about A must be 0 because the rod is in equilibrium. So mg ka torque, what is the perpendicular distance? I'll just draw the thing again if you want. This was tension, this was mg, and this was ft. You are trying to find the torque about this point A here, and this was your theta. Extend the line, drop the perpendicular. Isn't that how we find that? That is L by 2 sine theta. Same thing, extend the line and drop the perpendicular. How much is that distance would be? This is x by 2, so this distance will be L minus x by 2 sine theta. So torque about A will be 0, which will be basically mg into L by 2 sine theta. That must be balanced by the bind force ka bind for torque L minus x by 2 sine theta. Interestingly, theta cancels off. M is nothing but density of the rod, area of the rod, length of the rod, that is your M, G, L by 2. Bind force will be rho by 3, area of cross section. Only X part of the rod is inside, so that is X. G, L by 2 minus X. To check out the statement there. So bind force is simply the weight of the displaced liquid. So A gets cancelled, G gets cancelled. Rho also goes off. This would be L square by 2. 1 by 3 L by 2 minus X. There's one X also sitting here. A goes off. Rho AG. Rho AG. Perfect. L square by 2. 1 by 3 L by 2 X. Okay. Simplify this. L square by 2. Lx by 6 minus x square by 3. We got a quadratic. Multiply 6 everywhere. You get 3L square is equal to Lx minus 2x square. 2x square minus Lx plus 3L square is 0. X is equal to L plus or minus root over b square L square minus wait. When the hell did this become L by 2 minus x? This is L minus x by 2. Shit. Should try. I was getting imaginary roots. That is how I realized something went wrong. X is equal to 2L plus or minus root over B square 4L square. I'm still getting imaginary roots.
सर
Ah,
सर वो डेंसिटी रॉड और पानी का उल्टा है.
yeah, you're right. Hmm. L square by 6. XL minus X square by 2. It can't be plus because X can't be greater than L. What is root 24? 2 root 6. 24 by 36, no? 12 to the 12 threes. There, that's your X. Phew. Clear this? A lot of calculation mistakes today. Once you got the X, your job's done. Then you can say tension is equal to mg minus fp. Mg of the rod is rho by 3al g minus buoyancy force will be rho a xg. Substitute, get the answer. Now, if you see this answer, what you got is independent of theta. You cannot find that theta. I need more information. That means depending on at what point you're tying the string, the answer will change. So what this question is telling you is, suppose if you keep the block like this, when you suspended it here, this height h was there. So the theta actually depends on this height h. This will be x inside. Suppose if you tied it like this, much higher. Yeah, the diagram is not up to scale. Your theta will again change, but this will remain same. You're getting this? So there was a question like this. Suppose if you catch one end of the rod and if you slowly start pulling up, what happens? That x will always remain same. So if you are giving me this h ka value, right, I can then find. So theta depends on that h. Height where the rod is suspended. Because think about this, the theta is always cancelling out. It doesn't matter whatever is the theta and the torque. Is that clear, everyone? It won't be so much immersed, but then you got the idea. Clear this? Harry, I remember we did a problem like this. There. So that is the thing. So take a break. Come back by 9:40. We'll continue from here. Any doubts so far? Sure. Come back by 9:40. Comes on everyone. There. So till now what we did, right? The fluids were always at rest. So that's fluid statics. The next part, fluid dynamics. So in fluid dynamics, right, we study fluids in motion. Everyone comes on. So when you have a fluid, what are you exactly studying? We are not studying each and every molecule. We are studying a small section of the liquid. We call this thing control volume. It's just a hype, a name just saying a small part of the liquid. So a control volume is simply the region in which the liquid is studied. So what do you exactly study here? Like, in fluid statics, when we studied pressure and this thing. So here we study flow variables or field variables. Just give me a minute. I'll just kick out all the people whose cams are not on, then we'll continue. Yeah. The first thing we study pressure. Then we study velocity of the liquid particles. So whenever you study a fluid in motion, these are the quantities which you want to study. Density. Now, luckily, we take ideal fluids, so density doesn't change. But in reality, when the liquids are flowing, because of the pressure also, right, density does vary a bit, but yeah, negligible. So when you say this liquid particle, exactly what's the particle there? So when you say a particle here, it is simply a collection of molecules. You're not studying speed of each molecule here. Every molecule will have different speed. But if you take a collection of molecules on an average, their velocities will look identical. So when you say speed of a liquid, right, you're not talking about a single molecule. We are taking a certain small volume, the average speed of all the molecules, right? That will be the average speed of the liquid there. So individual molecules have different speed. No. So when you study liquids, we define something called a streamline. Now, studying fluids is very difficult. right? If you ever heard about Stokes-Navier theorem, right? You have viscosity. Studying fluids is very difficult. Matlab, you cannot explain everything is just theoretically. In a real life, right? In the real life cases, the it depends on a lot of things. It depends on temperature, variation of temperature, density, the shape of the body, wind speed acceleration, and number of things will depend. So normally, whenever you're studying anything, right, in case of fluids and all, you have something called these wind tunnels. You make your prototype of the shape, you put it in a wind tunnel, and you check for all different possibilities. Theoretically, studying it is difficult. I think even mathematically, right, there is an equation Stokes-Navier theorem. Karke. It is one of the millennial problem. Ever heard about those millennial problems? There are 5 mathematical problems. I think one is solved so far. For everything that you solve, you actually get $1 million prize money. And then obviously, it is like for mathematician, that's like a Nobel Prize. So what is a streamline exactly? So what in our 11th and 10th, what we do, we study a very special case of fluid mechanics called streamline flow. So a streamline is a curve which is a tangent to the velocity of the liquid. At that instant, that's a technical definition, but let me tell you what it means. So basically, a streamline is the path of the particles. So when a liquid is flowing, the path taken by the particles is called a streamline. And the velocity vector is tangential to the streamline. So when a particle is going in along a path, the velocity will be always tangential to the path. Let me show you some pictures that would be better, you'll understand. So if you say this is a streamline, so the velocity at this point is VA. So when it is here, the velocity is VB. Now understand the meaning of this. In a streamline, the velocity at a given point is constant. That means all particles that reach A will have a speed VA. Anna, can you keep your cam on? And becomes VB at P. I'll give you an analogy. So think of like this. Imagine you have a highway there, and on the highway now there's a speed limit. At this point, the speed limit is 30 kilometers per hour. At this point, the speed limit is 50 kilometers per hour. At this point, the speed limit is again 20 kilometers per hour. And imagine every vehicle is following the speed limits. That means every vehicle that comes here will have a speed of 30 kilometers per hour. That same vehicle, when it goes here, the speed becomes 50. That same vehicle, when it goes here, the speed becomes 20. So speed of the vehicle is not constant. Speed of the vehicle can change with time, but speed of the vehicle at a given position is constant. Are you getting the meaning with that? Velocity is constant with the position, but changes with time. So there is a difference. A body is accelerating. So on a streamline, velocity at a given point remains constant. Velocity is constant with position, but can change with time. So collection of these streamlines is called a streamline flow. That is what we are going to study. So if you take a collection of streamlines together, we call it the streamline flow. But let me show you something like, what does it actually mean? All great definition and all look nice, but it's called streamline flow or steady flow. There are multiple names for this, or laminar flow. They all mean the same thing. Now, few more properties here. Two streamlines will never intersect. Why? Because at the point of intersection, there'll be two tangents. And just now we made a definition, velocity at a given point is constant. So if there are two streamlines like this, at this point, this is the tangent. At this point, this is the tangent. You cannot have two velocities at the same point. Basically, this is not a streamline then. This is something else. Point of intersection, there are two tangents. Therefore, two velocity vectors at the same time. Second thing, higher the density of streamlines, faster the flow. If more streamlines converge at a point, that means the liquid is flowing faster. So if you have streamlines like this, the number of streamlines are same. But if you look at the number of streamlines per unit area, think of like this thing. Matlab, when your class is left, when the class gets over and all are leaving from the classroom, and if you look at the door, we all are moving, but at the point of door, if you see, right, the same number of people are crossing a smaller area, so people go much faster there, isn't it? As the area starts converging, people start leaving faster. So people near the door will move faster compared to this thing. This is VB and this is DA. Density of streamlines, matlab number of streamlines per unit area, it is not density. VB is greater than BA. Clear? Calculate, na Srihari. What are you talking, Srihari? What procedure? What you're talking?
Sir, how can we calculate the density of streamline, number of streamlines per unit area?
You can't find. Or you want to find?
Sir, you said this relation, no?
Yeah, so faster the more the streamlines, more it will flow. So you can find the speed. Now from the speed you can find. It is just a hypothetical definition, right? Streamlines karke.
Sir, so we can't count the number of streamlines.
You can't count. How will you count? What is a streamline? We said streamline is a point where the particles are moving. So what is the particles moving? If you take one molecule, it is one streamline. If you take two particles, I think the streamline is thicker. It depends on how small area you're taking, isn't it? You're getting it? What did we say here? The path of the particles. What is a particle? Collection of molecules. If I decide to take one molecule as one particle, if you take 10 molecules as 10 particles, then your streamline and my streamline are different. Right? So let's see now, what is the streamline flow exactly? Why suddenly you want to calculate the number of streamlines? Just like that. It's like asking, if I give you, let's say, 1 liter ink, what is the length of the line you can draw? If I draw this thick line, then something else. If I draw this thin line, there'll be a different length. Getting it? So it depends on how much you're choosing. So listen, this is the important thing. So end of the day, all the definitions are great, but what is a streamline flow exactly? It's a simple way to understand. If you ever seen a traffic, right, flowing on the Eastern Expressway or the Western Expressway, I know people don't go properly, but technically people should be following the lane discipline. If you're going from one lane to another lane, you're supposed to give a signal and go. You just can't go however you want. But people don't care. But let's say people are actually following the lane discipline. This is what you will notice. If you take some ink and if you drop it on a streamline flow, you will notice this entire line becomes red. And you'll observe the ink does not spread. Meaning, for example, if there's an accident in one lane, only that lane will have a traffic jam and remaining lanes are unaffected. The streamline flow is like that. A neat traffic flowing on an expressway. So if you do anything to one streamline, the other streamlines are not affected. So only that will go. Now the opposite of streamline flow is your turbulent flow. Turbulent or non-steady flow. This thing is like your, ever went to your nearest market, Cow Gully, or this station road kabhi gaya? Go to any near the station and see how people walk and how the traffic goes. Anyone goes anywhere they want. Matlab, you don't know where that auto guy is going to go. You don't know where the scooter guy is going to go. People are just mixed up. Like, everything is going everywhere. These are not streamlines. They're crisscrossing literally. So in this scenario, if you try to put a streamline, ink here, if you drop some ink here, you will notice after some time, the whole thing, the ink spreads out. Because the particles have no defined path, isn't it? So that particle can go from one point to another where, and the whole thing spreads off. Are you getting the meaning of this? So when the flow is turbulent, all you need is a small drop of ink and the whole thing will spread out. When you're going in a streamline flow, the flow is pretty steady there, and it only follows the streamline there. What will crash into each other, Shrihari? What doubts you're getting, boss? These are
Sir,
molecules getting mixed up.
yes, sir. But in real life, you said no that vehicles go near the.
That is just an example for you to explain, right?
Yes, sir. So if they crisscross each other, won't they crash?
You don't know how the traffic goes on road. You never rode a cycle or something in a traffic. You keep crashing with everyone because someone is coming in front of you. You do that? मतलब अगर तुझे एक तार का कार दे दिया बस हो गया. You'll take the car and start crisscrossing, crashing, and you will decrease Indian population by half within a year. ऐसा कुछ plan है? You should do that actually. तुझे एक तार का कार दे देंगे and छोड़ देंगे स्टेशन रोड पे. You will not stop. You will not let them pass, or they won't stop. You will just crisscross them and dash them and ऊपर चढ़ा दो उन पे. Seriously, just an example, रे boss. Understand now? Why are you you're taking things pretty seriously there? That is just to give an analogy how the roads will look, and I was just trying to show you this is like an expressway and this is like your traffic near the station road. That's it. You're so innocent, Ray. So next time when someone comes in front of you, give them way. Or if you're in a bigger car, you just crash them and go inside. You are not in Delhi, right? So you can't do. Mumbai mein nahi chalta hai. So if you're in Delhi, you can do that. Mumbai people are good. They give way. You're from Mumbai only, right? So then you are safe. Now, who decides whether the flow is streamline flow or turbulent flow? We have something called Reynolds number. Now, technically, this is removed from the portion. That's what they say. But You'll get this in bits, or CET, or they will ask this anyway. Rho Vd by eta. Let's see what it means. So when a liquid is flowing here, V is the velocity, rho is the density of the liquid, and d is your diameter. And eta is the coefficient of viscosity. That's our next chapter though. Coefficient of viscosity is just like friction, like higher the coefficient of viscosity, more friction the liquid has. So using all these things, we calculate the Reynolds number. If your Reynolds number is less than 2000, I think this we need to check the NCERT. NCERT, they gave a different number. Online there's a different number, but okay. The flow is streamlined. I think NCERT it is given 1000, I guess. If your Reynolds number is between 3000 to 2000, right? This is we can't say anything. It can be anything. It can be streamlined or turbulent. So just roughly have an idea there. If you higher the Reynolds number, the flow becomes turbulent. If R exceeds 3000, flow becomes turbulent. Again, completely experimental. We don't have any proof or anything for this. So there was a theoretical question like this. For a liquid to be in a streamlined flow, which of the following options are right? Look at the options. For the liquid to be in a streamlined flow, which of the following options are right? It should have low density, low viscosity, high density, high viscosity, high density, low viscosity, low density, high viscosity. That's our options. Though. It should have what? Density low or high? Viscosity high or low? If you want a liquid to flow in a streamlined flow, it should have what density, high or low? It should have what viscosity, high or low? Look at this. For streamlined flow, the Reynolds number must be small. And the Reynolds number is rho Vd by eta. Matlab rho is in the numerator. So you want Reynolds number to be small, so density must be low. So numerator must be small. Denominator must be big. Low density and high viscosity. Standard question, right? Clear with this. Now, why do you need this term, this thing? Think of like this. Imagine you're making, some solution for eye drops. If you ever seen your eye drop, if you see your eye drops, right, if you read the label behind it, they have some different things. They have something called solvent, right? They have something called active ingredient, and they have 2 to 3 substances. Now, when you're trying to mix them up, how they mix it up. So you have, let's say, solvent here, and you have the active ingredient here and everything. Now you tell me, when you want to mix this, do you want them to flow in a streamlined flow or turbulent flow? Let's say you're manufacturing eye drops and you have a solvent and you have an active ingredient, 2 chemicals. Do you want them to go in a streamlined flow in a pipe or go them in a turbulent flow in a pipe? So question comes like this. You want them to be completely mixed up or you want them to be like 2 separate liquids in the bottle? You want them to be completely mixed up, isn't it? That means when you're mixing them up, you have to send them in a pipe in a turbulent flow. Then what will happen? They will completely mix up each other randomly. And what you get at the end of the pipe is a uniform solution. Making sense? So, okay, this is 1000 it seems. So we will take it as 1000. Okay, then so let me show you how this would look. So they're sending the water there through a pipe. They have on the left hand side, right? They have a small thing. They're releasing ink inside. You can see the water how it is. It is bluish shade. So what is happening? The ink which they're releasing is getting mixed up with the water, and you can see the whole thing is giving that bluish shade there. And the liquid is also flowing faster. So remember, Reynolds number is rho Vd by eta. So if you have more speed, so you have more Reynolds number, the flow is becoming turbulent. So if you decrease the speed, can you see that? That's the streamline flow. You can see that Inca one single line going, neatly without getting mixed up. You actually observe this every day. Did you ever open your water ka tap? Next time observe karke dekho. When you open the water tap, the starting part of the water looks very clear, and then the water becomes hazy. Ever observed? So the starting part of the water which is coming out slowly. So the flow is a streamline flow. Once it starts falling a little, the speed increases and the flow becomes turbulent. So the water which is coming out of your tap, if you see, right, the starting part will look clear and the next part of the water will look a little blurry. There are actually two streamlines inside. They're not clear. That here you can clearly see how it is getting mixed up. Can you see? On the left hand side, you can see the streamline. As the speed increased after leaving the pipe, the flow has become turbulent. There, if you actually decrease the speed, you can see there are two streamlines inside actually. There you can see two streamlines. They're not mixing up. They're just going on like, it's like, the traffic on a highway, like they're just following their lane. This is that the liquid is going slower, so you can see them. But if you increase the speed, the flow becomes suddenly blur. There, see, the whole thing is getting mixed up. This is what I mean by turbulent flow. The particles are mixed up so much, the whole thing color changes. Then this is there, but I think it is the same thing anyways. Yeah. Everyone clear? What is the streamline flow there? No, we will not study the turbulent flow. We will limit our study to very special case. So we will study streamline flow in ideal fluids. That makes our life easy. So what are ideal fluids? There should be no viscosity so that I can conserve energy. But in real life, liquids have viscosity. The liquids are incompressible, meaning no matter how much pressure you apply, the liquid should not compress. Why do we need this? So that we can keep density constant. If you apply a lot of pressure and the liquid gets compressed, density gets messed up. We don't want to deal with that. Next thing, the liquids must be irrotational. What is irrotational? Ever seen in a water? Sometimes you get whirlpools. If you put your hand in a bucket of water and if you just try to drag it, you will notice, there are like small whirlpools you get. This is a rotational flow. We don't want this. So basically here, the streamlines are getting mixed up like this and going. These are not, things will get messed up. So we don't want to deal with these three things: viscosity, incompressible fluids, and irrotational. Clear with this? Great. Then, how do we find the streamline equation? We can't count how many are there because it depends on the thickness, but we can find the equation of the streamline. So the idea is simple. What is the streamline definition? The velocity is tangential to the streamline. So if this is your velocity, this is your Vx and this is your Vy, and this is your angle theta. The slope of the tangent right is tan theta, which is the vertical component of velocity by horizontal component of velocity. And we know tan theta is nothing but dy by dx. So dy by dx is Vy by Vx. There. Using this, we can get the equation. So let me show an example. So this is how they'll ask a question. They will say the velocity of a streamline is given by 1 by x I cap minus 1 by y j cap. When you look at this velocity here of the streamline, depending on your x and y coordinate, the velocity at every point is changing. This is your Vx and this is your Vy. The slope of the tangent is Vy, that is 1 by y by 1 by x, which is minus x by y. Slope is nothing but dy by dx. This will be y dy is equal to minus x dx. Integrate on both sides. This will be y square by 2 minus x square by 2 plus some constant. So this comes out to be x square plus y square is equal to constant. This is the equation of the streamline. What is this? This is actually equation of a circle. So if you have x square plus y square is equal to constant, this is the equation of a circle, in case you don't know that. So that means, how are the streamlines here? If someone asks you to draw the streamlines, this is how the shape will look like. So depending on the constant, so the streamlines are actually forming circles. It's a weird flow. They're not intersecting. So the liquid is just flowing in circle, circle, circle. This is how the streamlines will look like. Can you tell me, is the flow clockwise or anti-clockwise? Are the streamlines going clockwise or anti-clockwise? Look at this equation here. In the first quadrant, x is positive, y is positive. So in the first quadrant, if x is positive, this would be your Vx. Y is also positive, so that means Vy is negative. That means the velocity is actually going this way, isn't it? So the liquid flow is actually going this way. It's flowing anti-clockwise. Yeah. All clear with this? So this is how they'll ask you. They'll give an equation. They'll ask you to draw the, what you call draw the picture of a streamlines. Now I'll give you one. You guys give it a try. But got what to do? Idea is simple. The velocity I gave you will give you the slope, and slope is dy by dx, and integrate. Now you guys try this. Let's say the equation of the streamline v bar is given by a plus bx I cap minus by j cap. A and b are constants. V is the velocity of the particles on streamline. Find the equation of streamlines. What is the shape of the streamlines? Now, Max May, they must not have taught you at conic sections yet, but once they teach you, you'll be able to get all this stuff, like what is that equation and all. By any chance, they started conic sections for you? Circle, parabola, hyperbola, all that stuff. And then they will take time, I guess. They'll do it later, right? Yeah. But at least get the equation still there. I'll show you. Try it. I'll give you a minute more. Let's see. The slope is Vy by Vx. Vy is minus By. This is A plus Bx. Dy by y is equal to minus b dx by a plus bx. Hope you remember this integration. This will be ln y. This is minus b, 1 by b ln a plus bx. Plus constant. I'm not putting any limits here. The bb will cancel off. This will be ln y plus ln a plus bx is equal to constant. So this will be y into a plus bx is equal to some constant. So that's your equation there. This is actually an equation of a hyperbola. So we get, did you guys study this? Remember in chemistry, PV is equal to constant? If you have studied that, remember how does PV graph look like? It looks like this. Yaad hai? This is called a rectangular hyperbola. And these things which you studied in chemistry in a PV graph, this is called an isotherm. If you have studied that. So if you see the equation kind of looks like that. So we have y is equal to constant by a plus bx. So just try to look at the equation here. If you put x is equal to 0, you get y is equal to c by a. And at x tending to infinity, y will tend to 0. Meaning this streamline, first of all, will depend on the constant. You can actually take even x negative also, but I'll just do it for positive. Look at the meaning of this. If you take some constant c1, so it starts from here, and as you get closer and closer to the origin, you're just getting it, but you'll never touch the x-axis. If you take a point c2 here, it's again getting closer and closer, but it'll never touch. This is c3 here. It is again getting closer and closer, but it'll never touch. So c3 is greater than c2 is greater than c1. So it depends on c ka value. Since you didn't tell me anything, right, the thing would have looked like this. If you take c negative, same thing. So this is how the streamlines would be like. So that means the liquid is emerging from the y-axis and it is converging at infinity on the x-axis. Clear with this? Similarly, if you have taken x negative, then you would get something like that. But I think okay. This is how the streamlines would look if they ask you to draw a picture. E power c is a constant, right? C is a constant, so e power c is also a constant. So c is some constant. Now that constant has to be given. If you don't tell me the value of c, I don't know which line it is. Depending on the value of c, I can get whatever equation here. All clear with this? So the simple question would be, these are actually all rectangular hyperbolas. Those kind of questions they do ask, what is the shape of this thing? Circle, parabola, hyperbola, ellipse. More of a mathematical question. All clear with this? There, that's a bit about the streamline. So there, what is the end of the streamline? So streamline is simply the path of the particles. So basically in fluids, there are two types of flow, a streamline flow and a turbulent flow. So in a streamline flow, the particles are following some, proper paths. So we call this path as streamline, and the collection of streamlines is called streamline flow. Whereas in a turbulent flow, particles are just going however they want. We have no idea where will this particle end up here. Meaning, imagine if you leave particles continuously, let's say you leave particle 1, maybe 1 will come here. If you leave particle 2, 2 will come here. Particle 3, it will come here. So you can't tell where the particle is going to end up. The flow is so turbulent and random. So things get mixed up thoroughly. So this is decided by the Reynolds number, and then this is the equation of the streamline. Clear with this? Okay, with that we'll wrap up further times. Next class when we catch up, we'll continue from here. We are going to see something called equation of continuity and Bernoulli's theorem. So that will be the major part of dynamics, fluid dynamics. Okay, with that we'll wrap up further day. So you can any doubts, anything else, please stay back and ask. Also, you're free to leave. And do remember there's a test online till Friday, so make sure to give it. Tomorrow is a deadline. So any doubts, anything